Wednesday as well. So last time we started talking about poroelasticity. Mainly we have these three assumptions: that there's an interconnected pore system, that the total volume of the pore system is small compared to the rock, and that the pore pressure, the total stress, and the stress, total stress externally and the total stress on the grains are statistically defined, which basically just means that we can use averages, that there's a separation of length scales so that we can use homogenization or averages, okay? And then we define this basically effective stress, and I gave two definitions. The classic Terzaghi definition, which is the one we've just been using, that it's the basically the total stress tensor minus, I'm not sure, I thought of this, I don't know if it's just not showing up, or maybe I didn't put it on there, but there should be some indication that this is an effective stress. Sometimes we use a single kind of prime symbol for that, and possibly a double prime for this one. I think that I had them there, and maybe they're just not showing up on the screen for some reason. So you have the total stress minus the pore pressure, and the pore pressure only acts hydrostatically. So we just subtract it from basically the diagonal entries, hence the identity matrix there. And then in this exact effective stress, we have this extra coefficient right here, and this thing is called the Biot's coefficient. And I just want to sort of go over where that comes from, or how we come up with that. It shows up a lot, and it's important, particularly in shales and hard rocks. In unconsolidated sands, it's typically about 1, so it recovers the Terzaghi definition. But for shales and other sort of harder rocks, it can be 2/3 around that value or something like that. So I'm going to go over the derivation of that. Okay, the derivation is probably a little bit beyond the, it's a little bit beyond the scope of this class. I mean, I'm certainly not going to ask you any test questions about the derivation, but since you'll see it so often, I do want to show you where it comes from, and that it's not just, magical. So in our poroelasticity model, right, we have our sort of characteristic volume of material, and now the material has pores in it. Right? Of course, I've drawn these pores much larger than they actually are, given our assumption that the pore volume is small, right? And so we have some external stress that's going to be acting on this guy. And we'll just call that P, right? And then we also have a pore pressure, we'll call P. And the pore pressure acts normal to all faces of any pore, so that's also P. So if we look at a little characteristic piece of material right here, right? So we're going to take this material that's completely solid, right? So this is sort of a structure or a system, right? It's the solid material plus the pores. But this little black area I colored in, that's just the solid material, right? That's just rocks. There's no pore there, okay? So if we pull that out and sort of look at it characteristically, it's also going to have an external stress on it. And what's it going to be equal to? What's the external stress on this little piece of solid material that I've pulled out from my skeleton here? Well, if this is P and that's P, and this is in equilibrium, it's not moving, what is the confining stress on that little piece going to be? What's it going to be? No. I've got an externally applied stress of P. There's an internally applied stress from the pores of P. The thing's in equilibrium. So what would the stress on that be? No, it's not zero. It's P, right? If I'm pushing on the outside of something, quite frankly, even if the pores weren't there, right? If I have a piece of homogeneous material and I apply an external stress of P, and then I cut out any little piece of that material, the stress on it is also going to be P, right?
I think it's just the presence of the pore pressure.
Okay, so even if the pores weren't there, it doesn't matter for the argument I'm going to make. So that's also P, right? So if we write, well, we haven't really done this, but we can take any stress tensor, and I'm going to use this indicial notation that I've introduced when we talked about constitutive models. So I and J are just indices that go from 1 to 3, right? So if they go from 1 to 3, then there's 9 components total, okay? So the stress can be decomposed into a deviatoric stress plus an isotropic stress. And the decomposition is like this. And again, this is sort of why I said this derivation is beyond the scope of this class, because I introduced some notation that is not real familiar, and it's called Einstein indicial notation. And specifically, what's sort of unique about it is that anytime you have a repeated indice in the product of a term, like, so this is, the product of 1/3 that thing and that thing. Anytime you have a repeated indice and an indice that appears twice, that's the same thing. It's just a shorthand for this notation. So it's just shorthand for a summation. So Einstein actually introduced this notation that anytime you have a repeated indice, you don't want to carry around all these summation terms all the time. So he just said anytime there's a repeated indice, we're just going to drop that thing. So since this is repeated, what that really means, sigma kk is equal to 1, 1, 2, 2, 3, 3. Right? So I have this stress that, I haven't told you what this deviatoric stress is yet, but so I have the stress is the sum of the deviatoric stress plus the isotropic stress. So the deviatoric stress is the stress associated with shears, and the isotropic stress is the stress associated with hydrostatic pressure. Right? And in my example here, in my example right there, right, there is no deviatoric stress. I'm equally confining this little cube by P on all sides. So I'm not inducing any shear. I'm just squeezing it equally on all sides. Right? Shear would imply some type of transverse deformation. Right? I'm just squeezing it equally on all sides. That's an isotropic deformation. And so in this case, this is just 0. It's just 0. And so just so I don't make a mistake in my notes, I'm going to you know, what we're doing here is deriving what alpha is, okay? So for the moment, for the sake of this derivation and this derivation only, we're going to assume tension positive. Tension positive. Okay. Normally in the rest of the class we'll assume compression positive, but for this derivation only, we're going to assume tension positive. And so the way I have it drawn, P is clearly a compressive stress, right? So in a tension positive scheme, that's actually minus P, right? So anyway, ultimately what we have here is that we're going to define the pressure as 1/3 sigma kk delta ij. And I think last time I told you what delta ij is. It's this thing, it's called a Kronecker delta. So when I equals j, it's 1. When I not equal to j, it's 0. When I not equal to j, it's 0. Okay, so it's sort of like the identity matrix. So if you think of these tensors as 3x3 matrices, this just implies ones along the diagonal. Right. Okay, so we have the pressure is this guy, and therefore if we plug that back into, plug this back here where this is 0, then we have that sigma ij is equal to minus P delta ij. Right. Now when we talked about linear elasticity, I gave you, there's this formula, it was at the bottom. You remember we sort of talked about the big C matrix for isotropic linear elasticity. But at the bottom of that page in the notes, there was a formula that was like the stress tensor is equal to lambda times the trace of the strain tensor times the identity matrix plus 2 mu times the strain tensor, where lambda is Lemay's constant, mu is the shear modulus. And of course, these are just elastic constants of which, for an isotropic material, you can pick any two, right? And so this is how I wrote it in that slide. But in this initial notation we're using here, that would just be sigma ij is equal to lambda epsilon kk delta ij plus 2 mu epsilon ij. Right. So this is the initial notation version of that. All right. And lambda is equal, and this is just straight off of that chart which relates all the elastic constants. Lambda is equal to the bulk modulus minus 2/3 the shear modulus. And so if I plug that in, I have K sigma kk delta ij minus 2 mu 1/3 sigma kk delta ij plus 2 mu. And if I rearrange that, then I get K so if you look at this term here, it's like the total strain minus 1/3 the trace of the strain tensor times the identity matrix. Compare that to the stress, and remember stress and strain are related linearly, right? So compare that to the way I defined this, right? I said the total stress is equal to some deviatoric thing that's 0 plus the isotropic thing. Well, if I take that and I subtract it over there, right, then I have the total stress minus this isotropic thing is equal to the deviatoric thing. And the deviatoric thing is 0. So if you compare those terms, maybe I'll just write it out. If I just rearrange this equation, what I have is S deviatoric, which is equal to 0, is equal to the total stress minus 1/3 sigma kk delta ij. Okay, so this is 0. We'll just compare that to that, and keep in mind that stress and strain are related linearly. So if this is the deviatoric stress, then you might call this the deviatoric strain. And if the deviatoric stress is 0, then the deviatoric strain is also going to be 0. Right? So this whole term is 0. So then I'm going to take this guy, plug it in there. So I have minus P delta ij is equal to K sigma kk delta ij. The delta ij's cancel, and ultimately, if I solve that, I have sigma kk is equal to minus P over K. And what I'm going to write a little subscript on my K, I'm going to give it a subscript S, because this is the bulk modulus of the solid material, right? Obviously, if I consider the material as a whole, the solid material plus the pores, which we sometimes call the solid skeleton, it's got the pores in there. Remember, the bulk modulus is the material's inherent resistance to compression, right? So it should be intuitively obvious that if I take a piece that's completely solid and I squeeze it, it's going to be stiffer than if I take the whole thing with the pores in there and squeeze it. Is that intuitive? No? Because, I mean, here you're having to compress solid material. Here you're compressing solid material plus some fluid inside, which is more compressible than the solid. Okay, so if we go back and write down the total strain tensor, again, write our equation, the total strain is equal to some deviatoric strain plus 1/3 sigma kk delta ij, and this is 0, then we have that the total strain of the solid is equal to minus the pore pressure over 3K of the solid delta ij. And that comes from just substituting for sigma kk the relationship we just derived for the solid material. Right, that just comes from plugging that for that. Right? Okay, so that was all just based on the solid material. Right? So now let's go back and consider our skeleton material. So now we're going to consider the solid plus the pores and how it might deform. So we had this generalized Hooke's law that said that stress is equal to C C I J K L epsilon K L. So again, I've dropped the summations, but there would be, since the K and the L are repeated, there would be two summations out here over K equals 1 to 3 and L equals 1 to 3. Again, you won't be tested on this derivation. So you sort of have to take my word for it, but we can invert this relationship. In other words, we can solve for epsilon KL, and what we'll call that is that d KL ij sigma ij, where d is sort of C inverse. So we just solved this equation, and then instead of carrying around an inverse, we just want to call that d. So then the total strain in our skeleton, epsilon KL, is equal to d KLIJ times the stress, and we're going to use our effective stress model. And here's where my tension, so this is the effective stress. By the way, I should have mentioned that this CIJK, these things are material properties, right? This is a matrix of material properties, okay? So in the isotropic case, this would just be a matrix that contained essentially two independent quantities, Young's modulus and Poisson ratio, or pick your favorite two, right? This is just the material properties, but what I should have said is it's the material properties of the entire skeleton, right? So if you go to the lab and you measure the rock system, the rock plus the pores, right? Which is really the only way you can measure it. You know, it's very hard. You know, rock is just made up of a bunch of sediments, right? So you'd have to essentially test like pure quartz, right, or something like that, to test what any individual grain is. Okay, so since it's the material properties of the skeleton, right, of the system, then this is where our effective. So the stress is really our effective stress, and then before I defined effective stress with a minus sign right here, that's because I was using a compression positive sign convention. For the purposes of this derivation only, I'm using a tension positive sign compression, so there's a plus there. Right? Okay, so this is the total strain. You know, if I go to the lab and I squeeze this thing, just apply loads, and I measure the strain, just like I have it drawn there, I have that. That's the total strain, okay? But there's also going to be some strain due to any strain in the solid material, and we already solved for that. It's up here. So then we're going to have minus 1/3 Ks P delta ij. So this is the strain of the skeleton minus any strain that's in the solid material only. And that's the total strain. Okay, so so now we're going to introduce our exact effective stress. So we're going to say that the exact effective stress is equal to sigma ij plus alpha p delta ij. So now we have introduced this alpha, and that's equal to Cij KL. Again, this is the material properties of the skeleton times epsilon KL. Now we have an expression for epsilon KL, so we're going to say Cij KL times d KL ij sigma ij plus p delta ij minus 1/3 ks p delta ij. And so since C and D are inverses, so since D is defined as C inverse, if I multiply, these aren't matrices, they're tensors, but the same rule applies here. If I multiply a matrix by its inverse, what do I get? The identity matrix, okay? Same thing applies here. If I multiply this fourth order tensor by its inverse, I get the fourth order identity tensor, okay? So just skipping some steps, C times D then just gets you sigma ij plus C ij KL P delta ij minus 3ks P delta KL. And over here on this side, I'm just grabbing this. So it's delta ij plus alpha p ij. Right? I'm sorry, so sigma ij. So you can see on both sides of the equation there's a sigma ij. So they cancel. And now every term that remains has a p in it. So they cancel. All right. Then I can multiply both sides of the equation by delta ij. So if I multiply delta ij, remember I multiply by delta ij. Remember this is really, now you have repeated i's and repeated j's. So this is the sum over I, sum over j, times this Kronecker delta thing, which is 1 when I equals to j. You can work it out if you want, but what you'll see is when you take that summation, this becomes 3. Right? So this thing here is 3, and this thing here is 3. And so ultimately, when you work it out, you get alpha is equal to 1 minus delta ij, Cij KL delta KL over 9 KS, okay? And we're almost done. If the material is isotropic, then this term becomes 9 lambda plus 6 mu over 9. And turns out if you look that up in the table of material property relations, 9 lambda plus 6 mu over 9, it turns out that that is equal to K, the bulk modulus, right? K. And remember, I said that thisCijkl is the material properties of the solid skeleton, right? So this is the K of the solid skeleton. Or sometimes we might say that that's KT for total. So it's the total bulk modulus of the solid plus the pores. Right? And so then if you look at what this equation becomes, ultimately 1 minus KT over KS. That's what alpha is equal to for an isotropic material. I think there should be a parentheses here. Anyway, so for an isotropic material, this is what alpha is equal to. So remember what I said, that for an unconsolidated sand, it's approximately 1. Right? Think about that. Right? And what is sand made of? Quartz. Right? So if you were to go into the lab and test the bulk modulus of quartz, this would be a very, very big number. Right? So if you have a very big number, and if you were to go to the lab and you test the bulk modulus of a million grains of sand, you squeeze those, and you measure the bulk modulus, it's going to be a number that's much, much smaller than. So the total bulk modulus, in other words, the way sand behaves as a bulk, as a continuum, right? If you pack 1,000 sand grains or 1,000,000 sand grains and you test those, of course they're going to move past each other. There's going to be lots of space in there, right? And so that material, that's going to be a number that's much, much smaller than that number. And therefore, this is approximately going to be 0. And therefore, 1 would be what's left. And therefore, for sand, unconsolidated sand, 1 is a good approximation. So I think that just says what I just said. For sand, the bulk modulus of the solid, or the bulk modulus of the sand, is going to be much greater than the total bulk modulus, so alpha is approximately 1. For rocks, shales, and other things, it's not uncommon to have a value around 2/3. So here's a plot that actually shows some real experimental data for Biot's coefficient as a function of pressure. So you can see that this isn't constant, and this has to do with the fact that usually the bulk modulus is not truly a constant, right? So for sands, you see numbers at low pressures approximately 1, and reducing some for higher pressures. Essentially, that's also intuitive, I think. If you have a bunch of sand and you compact it together first, you squeeze it together, you're sort of squeezing out all the looseness, right? The air, if you will. It becomes a more dense material before you then try to attempt to measure the bulk modulus, right? So essentially, you're getting continued densification here. That's also true of other rocks and other things because you're squeezing out the pore space.